Hi, Carmen.
Hey, Booty, good morning.
Yeah, good morning. How are you?
I'm doing well. How about you?
Yeah, good, good. Yeah.
Is our speaker Ernest?
No, no, it's an external speaker, Ashwin. Yeah, from
Oh,
Vanderbilt. Yeah.
okay, I'll hold off on letting any students in until we get him set up with screen sharing.
Yeah, you can accept anybody who is on the waiting room and he will join at 12. Yeah. Mm.
Okay, so you do want me to go ahead and let the students in before the speaker?
Yeah, yeah, because otherwise they will not, they might leave. So
Okay.
accept anybody who is coming. Yeah.
Yep.
Okay. Thank you.
No worries.
Hi, Dr. Ashwin. Welcome.
Hello, everybody. Yeah, how are you?
I'm good. I'm good. How are you? Yeah,
Good.
great. So, I think we will wait for 5 more minutes, Ashwin, for the people to join and start at 12:05. Yeah.
Are we recording this?
Yeah.
So, there were few videos which actually I will not show if it is a recording because we are not allowed.
Okay. Yeah. Welcome everyone to join our seminar series. This is the second talk for this spring, and we will start briefly in 12:05.
Should
Ashwin,
I?
you can, yeah,
Yeah.
you can share
Should I?
your slides and see if it works. Yeah.
And then PPT is here. Let's bring the PPT here. Okay. Yeah, I think I can see.
Okay. Perfect. We can see from here also. Yeah.
Check if the slide change also happens. Are the slides changing?
Yes.
That's good.
Okay. So I think we can start this seminar series. So welcome, Dr. Ashwin, for taking time to speak in our seminar series. I will go with your brief introduction. Dr. Ashwin is a research scientist at the Institute for Software Integrated Systems in Vanderbilt University, Nashville, Tennessee. Previously, he was a postdoc fellow at the Center for Educational Technology, IIT Bombay. With more than 11 years of experience in academia and industry, his research focuses on affective computing, learning technologies, computer vision applications, and human computer interaction, with significant contributions to video effective content analysis, multimodal learning analytics, and deep learning in education. He also works on ethics, privacy, and bias in AI driven learning technologies, particularly in K 12 education vision data. Dr. Ashwin has published extensively in peer reviewed international conferences and journals with over 50 publications and 5 book chapters. His work has received multiple Best Paper awards and he holds granted patents. He has also contributed to NPTEL, which is a national program on technology enhanced learning in India, delivered keynotes and conducted workshops. He is an active member of the Association for Advancement of Effective Computing, IEEE, ACM, and ComSAC. So, welcome, Dr. Ashwin. Before we start, the we will take all your questions after Dr. Ashwin will finish his talk, and we will have around 10 minutes of Q&A at the end of the talk. You can also post your questions within the chat or unmute yourself and ask directly with Dr. Ashwin after the talk. So let's start the talk today. Dr. Ashwin, the stage is yours.
Thank you so much. Yeah, thank you so much for the warm welcome. I want to know a little bit of the background of the participants here. So, are they aware of the data science, machine learning, deep learning, or is the mix?
Yeah, it's a combination of people from Mehar Medical College and also from our School of Data Science. So,
Okay.
yeah.
Okay, thanks. Yeah, I will manage accordingly because it's a technical paper, so I can go technical as much as possible. If it's not, then I can go non-technical as well. So I just wanted to make sure that. Okay. Yeah. Hello, everyone. So uh, this one is talks about the emotion recognition engines. So my area has been affective computing from past 10 years. So affective computing is nothing but understanding different types of emotions, feelings, expressions, and so on. So here there are so many advancements that has happened in this area, but how are we using in the education domain? So this is specifically with respect to the education domain. So what are the challenges that we are facing in the education domain? If the machine learning or the deep learning algorithm, if it does not detect or does not classify the expressions or the emotions properly, then what will happen? Okay, so to understand that, we need to understand the entire structure of how a machine learning, deep learning happens, how the data is taken, and all those details. So I will start slowly with the emotions, and then talk about in the education context what is emotions, and then I will talk about what is a bias. So how are we experiencing bias, and how are we addressing bias, and so on. So you can ask me questions in the chat as well. So I don't mind. You can feel free to interrupt as well. If you feel like there is an important question that is needs to be answered, you can stop me anytime. I don't mind. Okay, let me start with this. So this is a very famous question, which states that the question is not whether intelligent machines can have any emotions, but whether machines can be intelligent without any emotions. So emotions plays a vital role in any intelligent environment. So this is the one of the proverb which talks about why emotion is very much important in our day-to-day activity, and why intelligent machines should also know all those things. So the what do you mean by know? So there are various aspects to it. One is, as a human being, we can recognize emotion, we can express emotion, we can have emotions. In the same way, can a intelligent environment can also have those things? If it can have, then what are the various modalities with which it can perceive that? What are the various mechanisms with which it can analyze that and express it? What are the modalities with which it can express it? So we use five sensory organs to express. So how the same thing can happen with the intelligent environment? How can it do that? So there are various aspects to it. So we are focusing in this talk only with respect to the projected emotion. What do you mean by projected is, so what are the changes that happens is there are two cases. One is the spontaneous expression change that happens, the muscle changes, and all those things gets expressed through face, hand gesture, and body posture. So these are called expressed emotion. I can have a feeling of frustration, but I may not show it. But there are cases where I will show it immediately for a second, then I will stop it, right? So these are called projected emotion, where actually you can physically observe. So the idea is to understand these expressed emotions, which are projected emotions, in a learning environment. So now what are the things which are observed in a learning environment? So when you say affective state, it's a broader term with respect to the emotion, which is a state which happens for a longer duration than the basic emotion. Basic emotion generally happen for a shorter duration. For example, surprise. I cannot be in surprise for 1 minute, right? With this facial expression, it's not possible. The projected emotion changes, right? So in the same way, in a learning environment, what are the different affective states can happen? So if this is a complete list of affective states, do you really think, it's a question you can actually think. So do you really think the emotions, like basic emotions like fear, sad, surprise, delight, how often these things happen? Okay, when compared to the options like boredom, confusion, annoyance, frustration, and all those things. So now there is a trade-off, right? So few things happen very momentarily, very rarely when compared to a, say for example, if you are having a 40 hours class in a week. So in the 40 hours, what are the different types of expression that will happen? If you see the percentage of fear happening, it will be less than 1%, right? It rarely happens in education environment, that too while learning. So that is called academic learning time. Whenever the learning happens within the classroom is called academic learning time. During the academic learning time, it happens very rarely, right? Maybe a sudden surprise test where you are not ready. It can give you shock or fear. So something like that. So in this context, people try to understand the broader perspective. What are the majorly observed emotions in the classroom? Those are called learning centered emotions or academic emotions. These are boredom, confusion, frustration, delight, and engagement. Engagement is the flow with a pleasant one, facial expression, neutral to pleasant. And then frustration is little bit negative valence and negative arousal. And boredom is like, so valence arousal scales are the one which tells us the how much actively we are actually giving the expressions. The valence is nothing but how much pleasant and unpleasant you are, and arousal is like sleepy to how much aroused your feelings are. So we can actually represent all these 5 learning centered emotions on a valence arousal scale as well. So we can tell that if the valence and arousal is extremely high, both are positive, then it is a surprise state or a delight state, or if it is extremely at the peak, it's called eureka moment. So similarly, if the arousal goes very down, so it's like a negative, then it's sleepy. Sleepy is actually one of the forms of very negative emotions. So like that, we can actually provide all these emotions on a valence arousal scale. Now, this talk will revolve around 5 learning centered emotions, where actually these emotions are calculated using valence arousal values. So there is a mapping which I will show you in the coming slides, which actually tells that if the valence arousal values, which is actually from -1 to +1, if it falls under specific set of regions, so it belongs to particular set of affective states. Say for example, if the valence is above 0 and arousal is above 0 to 0.2, then it falls under engagement. So in the same way, so we can actually derive all these affective states using the valence arousal models. Now, what people have done to understand facial expressions. Now, body language, hand gesture, and body posture also tells the the emotions. Affective state can be understood that, because there are few involuntary movement we do with the body muscles as well. But this talk, I will actually, I restricted myself to only facial expressions. Now, what are the various analyses that are done as a whole? So people try to understand using sensors to understand their emotions. Like they put a sensor on the chair to see the pressure on the chair. They put on the eye gaze. So how much actually we are looking at a particular thing. If you are confusing, you are going back and coming in the 2 different locations, right? So that is the confusion state. If it is frustration, how the eyelid changes, the pupil diameter changes. So all those things. And then we have facial expressions. Then we have posture patterns, like when you are bored, how will you sit? When you are attentive, how will you sit? So they try to understand using various modalities and try to see that what are the affective states we can understand in a learning environment. Then the significant contributor is actually, if the face is visible, then face is the significant contributor. And where are they looking at is the second significant contributor. For that, there are various works which talks about trying to understand how the facial expressions is actually explored in a learning environment. But if you see all the studies, most of the studies are done on adults. So kids studies are little rare. The next thing is whenever any machine learning, so just like humans, machine has to learn, right? So how does it learn? So we have to tell that, look, this is the data and this is the class level, and you learn by yourself that if some pattern comes like this, then this belongs to this particular classification, right? So the same way, we have to provide the information to it to learn it, right? So for that, we have databases. So what we do is, we take a set of databases in a different learning environments and train a machine learning or a deep learning model to understand it. But till date, there are very limited databases that are available in the education. Hardly 3 to 4 are available. Even among them, the databases are actually of adults that are publicly available. So now we have an issue now. So if the data set is trained on adults and if you are running on the kids, the data distribution itself changes. Then the misclassification is obvious. Misclassification in the sense, so if say for example, I have to classify it as a engaged face, it might classify it as a confused face because it's not trained on those data. So it's not aware that this particular facial expression of a kid belongs to which particular pattern to classify. So that is the major demerit. Even if you see, these are emoTW challenges which happens in quite often in the conferences, which are like very popular conferences. Even there, if you see the faces, right, these are from Asian faces, Southeast Asian faces. Even though they are collected from here through online, but they are not from different demographics. So if you see Australian or a United States or a Europe faces, then it's hard to find in these databases, right? So there is a diversity requirement as well, which is missing. Now let's see what are the ways in which we can recognize emotions. So one is explain basic emotions, which are called happy, sad, fear, disgust, neutral. So all those things are basic emotion, which doesn't last long in a projected emotion, which happens for a brief moment of time. Plutchik's emotion gives a wide range of emotion patterns, which is like it has a derived emotions as well, like joy, and it has more complex emotion which stays for longer duration, right? So all those things like moods, those are called moods, which stays for like longer duration. Even he includes that in that. And we have learning centered emotions, and there are other types of emotion as well, like engaged, disengaged, interested, not interested. So these type of binary classifications are also used in the study. Now that if there are no databases available, so what are the various other ways to do that? So we have databases that are actually available for the basic emotions. We have plenty of datasets available in the public, and that includes faces from kids or different age groups as well, but not from a learning environment, but it's from a different context. They have collected in the crowdsourcing, publicly available with consent and all those things. So now valence arousal classification is actually trained because valence arousal can also be used to understand the basic emotions as well. So now there are possibilities that we can take a model which is trained on like millions of faces, or even if you take like a few architectures which trains on 5-7 databases which have like billions of faces. So now AffectNet or CK Plus or any other database, the standard database that you observe. So these databases have plenty of faces. They are taken from different environments, different age groups, different demographics, and so on. So now if we take such model in a deep learning, it's already learned on a distribution which is similar to our distribution. Then what we can do is we can fine tune the model and then try to see that whether it works for our environment or not. So the structure goes like, we have an affective computing model, and we have a computer vision model. What does computer vision model do is, it generally takes a database. If there is no database, generally we create a database. So how to say a facial expression, we have a code for that, facial action coding system. Or how to give a learning centered emotions. So we have a protocol, BROM protocol, Baker Rodrigo monitoring protocol. So we have such protocols and guidelines to tell that if you observe these things, then you have to annotate for this. Fabo is body action. So there are several guidelines like this. We will use those guidelines and we'll create a database. That is one way of doing it. But creating billions of data is actually complex, right? Because we have to do manually annotate them. We have to, at least two different annotators should annotate. Then we have to see the intra-rater reliability among them. Or else what will happen is it become biased to that particular annotator. So we have to have a number of annotators. And then we have to see that where they actually agree. And we have to take only those images and create a database, which is complex. So what people do is they take an existing database and then they take the low level features which are trained on that and change the last layers in the deep learning models. If non-deep learning or the non-machine learning group is getting bored or I did not understand, just ask me questions, I will explain more. Okay, so then we have two ways of understanding the expression. One is a posed expression, another one is spontaneous expression. Here we are talking about a spontaneous expression, where actually it's a projected emotion that happens because of some trigger. Posed is like we are telling you to give me a pose with this particular set of emotions and all. Generally, posed expressions and spontaneous expressions are significantly different. That's what is observed in the literature. So the way in which you show fear, when I say show me your fear face, is different from when you actually show your fear face. So that's why most of the studies happen on a spontaneous expression. So when it is single phrase and I am sitting this much close to the camera, right? Well, all the facial features are visible. If something like this is there, then a simple machine learning algorithm is good enough. So it takes all the features of the face and tries to classify into Ekman basic emotions. So these are like very old ones, old methods which are good enough. Haar cascades and all those things are good enough to extract the features and so on. Now, if it becomes a little complex, let's say, for example, you want to understand the complexity of the emotion, like entire range of valence arousal, including learning centered emotions, then machine learning may not be sufficient because it may not pick the facial features. Because machine learning generally we handcraft and we tell that these are the features which are required. And in deep learning, we tell the algorithm to find the feature by itself. So there is a complexity in different complexity in that. I will show in the next slide. So if it is complex, then what we'll do, we'll go with the deep learning methods. If there are multiple phases as well, we generally go with the deep learning. And if there are multi-modalities, then also we do. If there are multiple people sitting in a classroom, then it becomes group engagement, right? So it's not just individual and group. So we have to understand both. So this entire model is computer vision. So the entire thing of affective states with the computer vision actually falls under affective computing. Now, is it easy to identify images? There are various complexity and challenges in a visual environment. So if you can see, with cat, we have resolution change, pose change. You can see there is a black cat here, illumination change. We have deformation, we have occlusion, we have intra-class variation, and we also have background clutter. So we have so many variations in this. I actually have images with respect to students as well, which I cannot show. But we actually saw so many cases which maps to these variations, and it's difficult to train a model and tell, look, these are the different variation which can happen, but still it's a cat. You have to classify it as a cat. It's a different thing. So why we have to go with deep learning versus machine learning? So that I will tell you. So when you say machine learning, we actually handcraft the feature and tell that, look, if these features are there, if these attributes are present, highest contributing attribute is called feature. So we use the word feature for that, that's all. So any attribute that is used to do the classification. So we tell the attributes like, say, upper lid rise, that is the action unit 5. So they divided all the facial features and then they gave a name for that. So we have like about 90 features for the entire upper body. So facial action coding system actually defines that. And we say action unit 5 is upper lid riser and action unit 25 is lip pair. So now if these two options are actually detected in the feature analysis, then classify it as a surprise. So this is a machine learning method. So now how many features we have? Maximum 95 features, because that many action units are there. But when you go to the deep learning model, a simple deep learning model, to do the same classification, so it will have minimum of 138 minimum, a million parameters. This is a base model which actually does for the emotion classification. So when you have like 95 to 100 parameters to classify in a machine learning versus 138 million parameters, of course, this deep learning will be better if the complexity is high. So that's why deep learning models actually perform better. Now, why I'm giving all this context is we will be using it in the understanding bias. That's why. Now the next thing is, so now you know that deep learning is better for the emotion recognition in the complex learning environment. How do you know that the deep learning is working better or not? For that, actually, we have explainable AI, right? Where actually you can see that whether the whether the methods are detecting your facial features or not. If it is detecting your facial features, then this is an example for person re-identification. What exactly is it looking in the face to detect that? Is it looking for the entire face, or is it looking at only some part of the face? So this is an example where actually for person re-identification, it is looking at only this part of the face. Can you see my cursor?
Yes, yeah.
Yeah. Okay, so it's checking only this part of the face significantly to classify it as someone else. Like it's a person re-identification by one. So if it is this, this is recognizing only this part to tell that it's Ashwin. Okay, so now we have to understand that it's not wrong. Why it's not wrong is deep learning is capable of understanding very minute information, the lines on our head and all those things, right? So even that is sufficient. If that itself is unique in the entire data set, for me, it will identify that and it will store it. Okay. So now why it is important to understand is now diversity comes into the picture. If I have like 1 million faces, and in 1 million faces, my forehead region is actually unique when compared to other one. It has unique lines which is different from other ones. It tries to catch that particular feature and it tries to recognize it as Ashwin. So now someone else may come with the same feature. So then what will happen? We have to we have to add the diversities in the data, right? So the data set matters in actually identifying. It may be wrong also. There may not be a unique feature, but it tries to map to the unique feature that is available with respect to the number of epochs we run. So that is also possible. So with this, now we know emotion recognition, deep learning, and how to understand whether it works or not using these are called GradCam heat maps, where actually it will put heat maps on the weights where it actually considers to do the classification. So can we do emotion recognition like valence arousal classification in real time? So can we do that? If we can do it in real time, we can use it in real time application. Like when I'm learning a course, it can directly detect my expressions, and based on that, it can provide scaffolds, feedbacks, hints, and so on. Right? Can we do that? Is the question. Yes, of course we can do that. So this is the video. Yeah, I think I will play. Yeah. So the idea is to show that it can recognize the facial features in real time. This data is actually taken from the public YouTube, so which is publicly available. And then the frames are at 30 frames per second. At 30 frames per second, it is able to recognize the valence arousal values. And even if a momentary disgust is happening, it is able to recognize. Momentary confusion, it's able to recognize. So if you see the valence arousal values there in the top, so if it is positive, negative, and all, those are the changes that is happening. So this is the first example where we can tell that emotion recognition can happen on in real time using a facial expression. Is facial expression mandatory? No. The facial expression is a significant contributor. You can also use the body posture, hand gesture, and so on. So can we do that? Yes. So there, can we do it in a real time? Yes, again, yes. So if you see, this is a different learning environment where actually the students are doing an activity in the lab. And in this, it's taken from a different database, not from the previous one. So, and here you can see the classification is categorical classification, where they classify into engaged, discussion, and so on. So now, even if you see the previous case and this case, so this guy may be reading, this guy may be looking at the mobile, this guy may be doing something in the previous also. In the previous example also, there are possibilities that their expression may be different, but their words, what they speak, right? So that can be different. So we need to include entire set of modalities that are required to understand it. But sometimes what happens is one particular modality becomes significant contributor. That is enough to tell that whether they are really having that particular expression or not. So we choose those peak expressions to understand and use it in the analysis of what we do. So we try to understand students' self-regulated learning. Self-regulated learning is how best we can understand uh, ourselves and then improve ourselves. So that is self-regulated learning, which has cognition, metacognition, motivation, and the emotion aspects in it. Then we have socially shared regulation, where two students in a group learn how they learn together. For all those things, the affect aspect, right, the emotion aspects plays a significant role. Now the next question is, we know that now there is a database, but that is not publicly available for the kids, and we want to address this. How do we address this? There are two ways to address this. One way is a video that I will show you now, and the other way is applying methods to solve those one. So what is this method? This is called de-identification. So what is de-identification means? I can remove my biometric features from the face, but keep the facial expression and release that as a database to the public so that they can use that. This is one way of actually addressing if there is a bias in the paper. So if you see this, so based on the epochs, it keeps on changing, right? So I will stop here because it will run for 1000 epochs. Okay. So now what we are doing it is, so we are giving a kid's face here. I'm not adding face due to reasons, this one, IRB reasons. So if this is a kid face and this is his expression, and we can generate a new face which doesn't look like them, biometrically it's different, but has the same facial expression. Now we can create such databases and give it to the model to get it trained. Then what happens is the misclassifications becomes less. This is the one way of addressing a misclassification. So now we talk so much about the misclassification. Let's talk about actual bias, why the bias is happening and so on. So there are several types of biases which are possible. Here I am talking only about the algorithmic bias. Algorithmic bias is, as you have seen, I showed you so many databases, right? So in the databases, there are possibilities that the database can actually tell it in a different way. The features can get selected in a different way, where actually when you ask a question to it, it may actually give you a pattern that is not desired. Unintended or potentially harmful properties of the data that lead to a unwanted or socially unfavorable outcome. So this is one of the, there are plenty of definitions for the algorithmic bias. So people define it in very different ways with respect to each modality, each perspective, each environment, like healthcare has a different definition, entertainment has a different definition, education has a different definition. So these definitions are very different, but this is one of the definition which is widely accepted, which talks about what is an algorithmic bias. So end of the day, if the data is unseen, belongs to a same distribution where we are checking the output, so if you say train test or test image or validate image, if all this belongs to a same distribution and still we are running the code and we are getting undesirable answers, so then actually there is a bias in that. So there are so many examples for bias, which I will give you some examples in the coming slides. So say for example, if I ask ask a chat GPT to give me the set of people who actually learned about the data bias using the deep learning algorithms. And if it gives only the students who are graduate students, then it's a bias, right? An undergrad student can also know that. Grad student, I mean, even 12th grade student also nowadays knows that. So it should not give only the undergrad students. So that's actually an inherent bias which happened because all the training data that we did were actually the grad students, and we did not address that at a very base level. What you mean by base level is those parameters which I shown you, right, in the facial action coding system. So like that, we have set of features which are actually defining any classification significantly. And if we go there and address that, this bias will become reduced. So there are various types of biases: historical, representational, measurement, aggregation, learning, evaluation, deployment, selection, data, and label. So these are the various types of biases that exist. So I will give examples slowly once I have a lot of examples for that. Whenever it comes, I will give you the example. So right now we are actually looking at three types of biases. One is selection bias, data bias, and the label bias. Selection is actually the feature selection bias. So if I am surprised, so eyebrow raise is a significant contributor. What else is a significant contributor? That we have to see. And then eyebrow raise is also actually a contributor for maybe frustration, maybe something else. So now there is a intersection of features, right? So when features intersect, how will it work? So that is a feature selection bias. Another one is data set. The data set also induces some biases in that. Like if it is not, if all the, I gave you an example of grad students for the deep learning bias, right? So the same way, the data can have a bias. The third one is label bias. As an annotator, they might label it wrongly. So that also causes some type of biases. That is called label bias. So these are the significant types of biases which I have examples for in the today's talk. But rest also have examples. I will just share it with you all. So bias can occur in any type of modality, not just in the vision. So I gave you an example of GPT, which is a large language model. Now actually the log data. So in the log data, they found out that in an automatic essay writing, it automatically graded them as poor for female students who attended the private schools. So the automatic grading system had this bias. Similarly, there was a speech-based system where actually the algorithm automatically rated the native speakers of Arabic, Hindi, and Spanish people lower for the academic achievement when compared to the other country students. So this is a bias which was there in the speech modality. For emotion detection through log, not through the facial expression, through log, they found out that the students from the rural communities were actually given less value when compared to the urban students, when log data was given as an input for the model to do the analysis. So there are biases like this, it occur because of the data. It can be labeling, it can be feature selection, it can be anything, historical, or so all types of data that I mentioned, right? Historical representation. So everything is possible. Now, with this, these are the set of things which are explored well enough, but nobody explored in a learning environment how it happens for a student or a kid. That too through for the facial expressions in the project environment. The main reason because the data are not publicly available. So now we try to see that whether we can understand the bias or is there any bias. So when we ran the code, we found out that the misclassification has occurred, but we were not sure whether misclassification was due to bias or due to the model's inefficiency. So there is a theory behind it, so which I will tell. So there is a Hadwin's theory which tells that we first thing is unknown, where we don't know anything. Then once we do the analysis, we will know that. Once we know that, we have to address it. So once we address it, it goes to the fairness. It becomes a fair architecture. If there is a fair architecture, then equity comes into the picture. So this is the loop. So in the same way, first we have to find out that whether there is any misclassification or not. We found that there is a misclassification. We took two models that are trained on millions of images, which is state-of-the-art models, EmoNet and HS Emotion. And there is one more thing called iMotions, which people very frequently use. It's commercially available tool. Uh, there they use it to understand the facial expression, not just facial expression. It can collect multiple data in a synchronous way, like EEG, GSR, screen recordings, and speech recordings. Everything it can record. Okay, so these are the three things which we consider. One is Emonet, HS Emotion as a open source models, and iMotions as a commercial model. So we took and then tried to see what are the types of bias it occurs. Empirically, if we found out that selection, label, and data bias were significantly high in these algorithms. The reason behind that is the real life data doesn't belong to the learning environments which we are looking at. Then if there is a bias, how to address that? There is two ways. One, I can create a new data set and add it. That is the de-identification. The other way is use methods to solve that. Like you can tweak the feature selection attribute, you can tweak the data distribution attribute, and then try to understand. So we consider different learning environments. One is the Betty's Brain, which is a learning environment which is quite popular here, where actually the teachable agent, the students teach to the agent, where actually it learns by itself, and we have a teachable agent to help as well. So it's a very beautiful learning environment. And then here one student learns, and then it's a single student individual learning environment. We took some sample data of 41 students with like 3 days, which is approximately like million frames, which is a good amount of frames for all the students if we consider 5,000 minutes data. And it has a wide range of distributed ethnicity diversity. And this is another study where C to STEM. So in this study, again here also we consider that. So here, since they are wearing masks, I can show the videos. So here also we collected data of the valence arousal values using all the three: HS emotion, iMotions, and Emonet. And the next one is embodied learning environment. This video I will not show, but here it's very complex because students are running, jumping, they are shouting, because it's an embodied learning environment where they embody for the photosynthesis experiment. One can be water molecule, one can be leaf, one can be the rat, and one can be the root, one can be the there are all the attributes that are required in the photosynthesis. They can become that particular molecule, and then they have to solve the photosynthesis process by changing from one state to another. So this is that other learning environment. This is more complex environment. Here also we actually collected facial expression for all the students throughout, like 30 frames per second. So this is what I was talking about. We first, there is an unknown, then we go to the known bias. If it is addressed, it goes to the fairness. If there is a fairness, equity will be there in the learning environment. So now we are in the stage of unknown to known, because we know that there is a bias from the empirical method. Once we know that, we have to understand whether that is a bias with respect to which one, which category, so that we can address it. So if you address it, that is called mitigating technique. Once we address it, then actually the model becomes fairer. So end of the day, if the model has sufficient data, sufficient complexity, when compared to the input complexity, it performs always better. The issue is to give that particular information which is rich and good enough. So we have iMotions, we have HS emotions, we consider all the images. I will just check how much time I have. I have another 50 minutes, no? Or should I end?
No, you have until 1. Yeah.
Okay, fine, that's good. That's good. So then what we did is we actually took the faces. So how to take the faces of students in this learning environment? This is little complex, right? Because I have to track and find out this is the teacher's facial expression throughout. So similarly, I have to track this student's facial expression throughout. If the value changes, right, so then it's a problem, because I cannot take a CSV file which actually gives one time value of this student, another time value of this student, and it get mixed up, and this is not possible, right? So how to track a particular student and identify them as them? So that is called person re-identification problem. So person re-identification works in a different way. It has two components to it. The one component is it matches the patterns on the body. So all the color of the cloth, the face color, and the hair color, the face structure, the body structure. So all the patterns that are visible in a student, it will put a bounding box, and then in the bounding box, it will see all the patterns, and it matches that pattern to the input image for each frame and tries to find that whether that particular person is the same person or not. This is the first step. The second step is it also tracks, like in 4 seconds, in 5 seconds, this is every 5 second interval. In every 5 seconds, where is he standing? For every frame, where is he standing? Two cases. In every frame, the standing guy here cannot go suddenly here. He's not a flash, right? So he doesn't have that superpower. So he has to, in every frame, he will be in a minimum like centimeter, or maximum he can go up to like next one step, right? He cannot go beyond that within a frame. So it tracks based on the time. So there are two types of tracking. One is tracking based on the position. Another one is tracking based on the facial expression. Even our facial muscles cannot suddenly change like this within a frame. Within a frame is the 1/30th of a second, which is like the milliseconds wise, which is very less for a muscle movement to happen. So now three things. One is tracking the facial muscles, tracking the position, and tracking the, uh, I mean, addressing the entire body patterns or the things. All three things are considered to do the tracking. So even in the tracking, it's like only 90% accurate. Why? Because there are occlusions. Some people go and come back. Two people look alike because they are wearing the same dress with have same skin tone. So we have those cases where actually the method significantly fails. Then what we did is we manually corrected it because this is an emotion recognition problem, not the re-identification problem. We just wanted to find out the emotion recognition for them. And then we at the end had 9.18 million image frames, which is like a significant amount of data. And how to we cannot manually verify. Manual verification is practically impossible, right? Then what we did is, since these are actually state-of-the-art models, we compared where HS emotions or the emonet does not match with the I emotion values. If those two disagree, right? So then we have a problem. So 83% of the time they were consistent. 16% of the time they differed. 16% is still like huge number. So again, we cannot do the manual validation. So what we did is we took all those data, ran different methods on that to find out. So the first step is pre-processing, where we actually excluded all the occluded, blurred, and uncertain images, and then classified everything like happy, neutral, sad, everything we classified as different architecture, HS emotion and emotions, and try to see this misclassification and try to understand it using various techniques. One of the first technique is the grad cam mechanism, where actually we try to see that when the misclassification happened, why is it misclassification happening? And we can actually use a confusion matrix to see that where and all these misclassifications are happening. So then we found out this. So this is a confusion matrix which tells that where the misclassification happened. Okay. So if you see, the SAD is significantly misclassified with the confusion. SAD is significantly misclassified with the confusion. SAD is also misclassified with anger more, and confusion got misclassified with the sad more. Confusion also got misclassified with neutral, and neutral and happy have some misclassifications. So the higher I mean, you can see this color. So if it is blue or dark blue or beyond that, so it is like a high rate of misclassification. If it is these colors, then there are less chances of misclassification. So we saw that there is a significant misclassification, so which is happening. So now why is that happening? So we use the grad cam to see that. So I cannot show the heat map of image because it's kids image. That's why we draw only where the heat map significantly, like blue region of the initial image. That's why I showed that blue region. So now if you see that, it is considering only some parts of the image for doing the classification. So eyes and eyebrows you can see, nose you can see, a little bit of lips, right? So not much. So no other body, I mean facial expression out of all the action units that are observed while doing the classification here, right? If you remember, so we had action units like this. So inner brow rise is one action unit, upper lid riser is another action unit, outer brow riser is another action unit. So we had plenty of action units like that, right? So it was not recognizing these action units. So that's why the eye motions were giving different answers. So this is what the eye motion results, because eye motions also works with the, it has a deep learning model, but it significantly works with the facial features like the action units. Then why is this happening? So this bias was happening because of this reason. So there is a overlap of action units. Say for example, confusion AU4, which is this one. This one is AU4. So if I make the eyebrow like this is the AU4, um, which is generally significant contributor for the confusion. But sadness can also bring that. Fear can also bring that. So if you see, there is an overlap of this. So sadness has 1, 4, and 50. Fear has 27 and 4, along with 2, 26, 1, and 5. And then anger has an overlap with confusion as well. Disgust has an overlap. So this is a feature selection problem where the feature is getting overlapped. If one feature is not getting recognized at that point of time by the model, it is not able to actually classify properly. So this is actually tells us that feature selection actually had a problem, and this bias is due to the feature selection. If you see, fear is actually getting misclassified with surprise most of the time. It is because fear and surprise, if you see, the surprise is a subset of fear. So if one or two features like 20 is not recognized or 7 is not recognized, then it can misclassify fear as surprise. So this is a feature selection issue. This is the first one we found out. And then there is a database issue as well. So all the databases that are done, so due to time constraint, I will make it a little quick. So since all the databases, these are the set of databases that are trained for those models, which are like state-of-the-art models. And all these databases doesn't have students from a learning environment. Their complex expressions are extremely different from natural expressions given in the wild in the outside the learning environment. So this is the next set of results. We also did statistical analysis to find out that. And then we have data selection and also label bias. Now, how to address that? There are two ways to address that. One is attribute aware, another one is entanglement. So what does it do is in attribute aware, so it will tell, look, for confusion, this attribute is very much important. If it is not there, then don't do the classification. So it gives a preference like weightage for the features. Disentanglement is for sadness, it tells that look, you just don't concentrate only on this one. You have to concentrate on all the three. So sometimes I will remove 4, sometimes I will remove 15, sometimes I will remove 1, and then tell it like, look, these are possibilities as well, but still it's a sadness, because for fear it's a problem, because fear has like so many action units in that. Fear should get trained to see that if 2 are missing or 1 are missing, all 3 are missing, still there can be a possibility that it can be fear, because fear has so many action units where the intersection for other action units is less. So two ways to do it is, one is attribute aware, another one is disentanglement approach. So both actually we applied for the data. Now apart from that, what we did is we did data augmentation as well, so that it enhanced the problem. So now what you can see is the initial baseline results was like 68%. After the data augmentation, for entanglement, we found significant results for many of them. Happy doesn't have much of a difference for anything, right? Why? Because if you see, happy doesn't have any overlap in the features much. Contempt is not there anyhow. So happy was like, it's a very easy one. Neutral can be associated with happy, because if 6 is also not detected, 12 is not detected, neutral is 0, right? No action detected. So it used to go to the neutral, that's all. So accept that for most of them data entanglement work, for sad data attribute aware work. So that's why I gave the example of attribute aware. For confusion also, you have to look for the this one attribute A4. So these are the results which talks about like how we can overcome this bias. Now we actually address the bias, it goes to the fairness. That is the structure. So this is a discussion which actually tells us that what are the various action units and where exactly it failed and where exactly it worked, for which gender, which race it failed. So we actually saw that for darker skin tones, the bias was significantly high when compared to the lighter skin tones. So there is a Fitford's scale for the skin tones. It's rating on 1 to 6, which tells from darkest to the lightest, like a brightest. So with that scale, we can measure the scale of the skin tone as well. So we found such issues which actually causing the significant contributor. Now I also talked about the viewpoints in the sense the angles, camera angles, if you keep that. So if you see that the camera angles, if you give the same expression and change the camera angle, the valence arousal values changes. This should not happen. Viewpoint variation. Though this is also an example of selection issue, where actually one type of bias which is happening. So then we have, this is for the eye motions, where actually we kept the normal lighting and different lighting condition, different camera angles, and different skin tone for the same expression. And you can see the valence arousal values vary significantly. This also tells that there is a significant bias. For eye motions, we cannot retrain the model. It's commercially available. That's why I'm just showing the results. For others, we address the model. So, and we found out that we can actually address it and we can get the better results. So with this, I will actually give the open-ended questions and stop it here. Like if somebody is using not just emotion recognition for deep learning, because this bias and all those things are actually good for any complex machine learning and deep learning algorithms, where actually the training data set is not complex enough and we don't have enough annotated data to train. So for any method or deep learning method to AI to be used in any environment, it can be healthcare, it can be education, it can be entertainment, or it can be any environment. So what are the things that we need to consider to responsibly use it and deploy it? That is the first one. How can we integrate in the analytics? That is the second set of questions. The third set of questions, when do you have to address bias? Is it at the initial stage of the development or after development? So these are very tricky questions, like open-ended questions, which is getting, still getting answered in the research community. Then what are the things which are required? Say, for example, do you have to address the hardware issue, or do you have to address the software issue, or you have to address both? And is expanding data set sufficient for the generalizability, or what are the other solutions, or what are the other possibilities? And how do we make sure that inclusivity and adaptivity can be included in these learning environments? With this, I will end the talk. Thank you so much for listening. Yeah, thanks everyone. These are some of the references, and thank you.
Okay, thank you, Dr. Ashwin. It's a wonderful talk, and I know it's quite a challenging problem to solve, like coming up with those emotion recognition in the real time, and like training the models on this large amount of data is pretty challenging problem in terms of computing. So I have just a couple of questions. For training your model, have you trained it from scratch, or you use some transfer learning approaches? Uh, and how accurate are those transfer learning approaches in your scenario? Yeah.
Yeah, we did not do training from scratch. The issue is because if a trained model is on like 1 million images and so on, so the low level feature extraction are very good in that. We cannot define a low level feature extraction with a small amount of data. So we went with the transfer learning itself. We actually changed only the last two layers, rest of them we freezed it, and then we retrained the model. Once we retrained the model, our accuracy was above 88% for the emotion recognition for our annotations, which was quite good enough and acceptable. And the reasons behind that is there are few cases where actually the expression itself is ambiguous. The annotators did not agree well. So if the human annotators, they themselves did not agree well, then the computer becomes more ambiguous. The other cases are there are complex structures. Like as a human being, if I see the face, if I see the particular image and tell, we can do knowledge transfer to understand so many complexities in the face. But the computer will fail to do that because it doesn't have the knowledge transfer component as of like well built now. So those are the two reasons where it's still failing. Because of that, we have a accuracy of less than 90. And what was the
Okay.
second question?
I think that was the only one. So the next
Okay.
question I have is, what are the biggest challenges that you faced during this project? Yeah.
Yeah, there are several projects. So we actually use the affector to provide scaffolds, hints, and feedbacks. That is one. That is the fun category of thing. The second category of thing is we try to understand their learning processes. self-regulated learning, when he's doing planning, when he's doing monitoring, when he's doing enacting, and what is the expression during that time. So all those understanding of like negative emotions, we call it negative valence and arousal valence are called negative emotion. Confusion, frustration, boredom, all these are called negative emotion. That does not mean that that will not help. See, confusion helps them to learn better. Frustration sometimes help them to perform better. So these are negative valence, arousal values. That's why it's called negative emotions. So what we found, what we initially did is, when we try to understand all these things, we found so many cases where actually it got misclassified, and we found like when the student was not even frustrated, he was getting the message like you are
Yeah.
frustrated, you are frustrated. That was making them more frustrated.
Yeah.
So even during the
It's
confusion aspects as well. So we found so many cases of mismatch where actually it wrongly interpreted the expressions, because
okay.
these state of the art models are very widely used. So then we found out like when it has to tell what is the peak moment where one modality itself is like good enough to tell and it's 100% sure. So choosing that using the proper clustering is a very difficult task, and we are still doing that, but it's, yeah, that is one of the
Okay.
major challenges.
Okay. Thank you. The floor is open for questions. I think Carmen, do you want to take the chat questions or?
No worries. Let's see. Okay, in the chat, we have a question from Nazira, who's curious if you did any analysis in accuracy comparison between ages and if your training images have good distribution across children, adults, and seniors.
So, Dr. Ashwin, it's on the chat, so you can also
Yeah, yeah,
read the.
I was reading that. Yes.
Okay. Mm.
Yes, yes. So one of the studies which we did was actually not in this, but we have considered ages. Like the even there was different age group, like middle school students versus high school students versus grad students. So there were a significant set of differences which we found. So what we did is we tried to make sure that as many data distribution with respect to the demographics as well as age is present in the training data. Either you can do it with the de-identification or with data augmentation or with adding multiple data sources to that. So we did almost all to reduce that, I guess. So we have done that. Do we have, also your training images have good distribution? Yes, we have a good distribution of that because we are collecting data from all the three ranges. We have so many studies happening in SSME schools, in MEX, we have the studies going on, and we have conducting studies in the primary school as well. So we have the proper sufficient data, but anyhow, we cannot share. So nobody shares the kids' data, and it's not good as well. So it's just that we can train the weights and we can release the weights. That's all. So the next question is, I think, on sentiment analysis. Sentiment analysis is similar to the affective state, but sentiment is not like, it doesn't have an involuntary thing because you are typing it, right? So it's more of LLM based work. So it works in a slightly different way. It's like positive, negative, and neutral. That is the best possible ways to tell that. It doesn't have much of a classification. So it's like a subset of the entire affective computing. That's all. But still, we can actually map the valence arousal values to the sentiment analysis. In one of the studies, we actually did that. We took the chart messages and transcribed the text, and emocap is a very standard database which has like conversations. So all three are there for the data set. We tried to fuse them. So what is the best method to fuse? In that, we actually did the sentiment analysis. And DADW, yeah. So data augmentation is actually to make the feature selection, data selection, as well as this one, selection of the features happen at a very better level. That's all. So we are fine tuning, or we are actually targeting the feature selection process itself to make it better. That is actually the DADW, entanglement and the attribute aware is doing.
Okay, great. So, yeah, if you have any questions, you can unmute yourself. Students, you're also welcome to ask any questions with Dr. Ashwin. Yeah.
Yeah, I think I stopped sharing, right? I'll do that again. So
Yeah.
if you have any questions, you can actually even mail me. So I will be happy to answer because very less people are working in this area. So if the medical school people work with affective computing, then I will be happy to see that work.
Yeah, we are mostly from the School of Data Science here, so I think
Mm.
most of the
Mm.
students are understanding. Yeah,
Oh, nice. That's nice. Good to know.
yeah, yeah. Mhm.
Yeah.
Okay. I I think just one more question that arises, Dr. Ashwin, is like, have you tried
Mm.
these generative models to
Yes.
mitigate this data diversity problem? Yeah, or
Yeah.
augmentation.
The first video which I shown where actually my face got changed to someone's face. That is a style gap, which is a generative
Hmm.
model.
Okay,
So we significantly use the generative model, transformers, attention models. So this help us a lot in actually making it more robust.
okay, okay, okay. There is another question from Andrews. Were
Yeah.
you able to identify what Spanish, Hindi, Arabic native speakers have in common to create bias?
Oh, I did not get your question, I guess. Um, I mean, we don't create bias. Bias will happen because of that, and it depends on the problem statement. If I understand your question correctly, you are asking that if three different set of people are there, and we are addressing an issue where these people's data is actually taken and trying to do something, then what are the possibilities that bias can happen in this case? So that might be the question, I guess, right? So it's mostly the cultural dependencies. If it is a speech based ones, right, the accent actually differs a lot. So what it does, it maybe the one which is closer to the English, the accent closer to the English may get actually a better interpretation and better one, and the one who is actually having a lesser accent which is close to the English may get a lesser evaluation for that. So it's possible that that can happen because they may not be. So Spanish, the number of people who speak Spanish is significantly less than the number of people who speak English. So data is of course imbalance. So when there is an imbalance, there are chances of bias is significantly high. I cannot do data augmentation every time. The problem is if there are 100 people and if I do data augmentation, the what you call the pattern in this 100 creates again a chaos and actually make it more robust. Yeah, if
Okay.
you don't ask the question properly, then just let know.
Okay. Uh, Thank you very much, Dr. Ashwin. I think it was a really informative session. I think, uh,
Yeah, my pleasure.
yeah, if you want to have any more questions, you can directly email to Dr. Ashwin. And look forward to our next speaker. Most probably, we will let you know when will be the next seminar session. And thank you, everyone, for taking your time to attend this. Thank you. Yeah, you all have a great day.
Thank you, everyone. Thank you for the opportunity. It's a pleasure.
Thank
Thank you
you.
all.
Thank
Bye
you.
bye.
Yeah.